Welcome. This is your final lesson for Chapter 4. So Section 4.8 is properties of logarithms. And the last video kind of covered what a logarithm is. So now we're going to use properties and get into graphing logarithms at the end. Here's what I'd like you to start with though. If you want to pause the video and just start with this warm-up. This correlates to yesterday, maybe a slight challenge in this one, but see if you can solve this equation for x. So first step is, because this is an exponential form, right? This is 5 raised to the x raised to the third. That's kind of the twist. Of course, you could guess and check, right? Just like try to, or graph it on your calculator and find the intersection. But if you need to show your work algebraically, because this is an exponential form, we can put it into logarithmic form to try to solve for this. So because the first base of the exponential function is 5, I can put this into logarithmic form. So I can do log base 5, because this base is 5, and then swing over, so log base 5 of 246, and that's going to equal the exponent, and the whole exponent is yet another exponent, so that's okay, x cubed. Okay, I can type in log base 5 of 246 into the calculator, talked about that yesterday, and I get 3.42. So if I rewrite that, x cubed equals 3.4207, round generously, so your answer is as accurate as it can be. And then when you have something raised to the third power, if we raise this to the reciprocal, which is 1/3, that will cancel out the third power. And then, of course, raise the other side to the 1/3 power. And you can see I did that on the calculator as well. And I got 1.507. Don't forget, you can always check your answers. So put 1.507 back up into this equation and for x, and you should get 246. All right, on to some properties. So before we get into the properties, just because you're going to be using these throughout today's work, making sure, and the warm-up probably refreshed you, but here's the definition of a logarithm. Okay, so if you have something in exponential form, you can then put it into logarithmic form as well, vice versa. So you can make sure you're comfortable with that, nothing new. If you have a logarithmic function with numbers, here's an example, of course. So log base 4 of 64 equals x. In exponential form, that's equivalent to kind of swing it over. So 4 to the x equals 64. And then you can probably see easily that x has to be 3. Same thing if you're in exponential form. You can put it into logarithmic form by translating the base. So base of 2, log base of 2. And then again, this kind of swings over as well. So log base 2 of 32 equals 5. So just taking a moment to make sure you're okay from yesterday, or if you got behind or something, just to refresh you on that. So now onto our laws for logarithms. There are 3 of them. So I'm going to just do one of them at a time here. So the first property of a logarithm, and I will also give you an example. In blue here, it says if you take the log of any product, like A times B, you can separate the product with addition. So I can write log of A plus log of B. Now notice when you use this, it expands it. So the one log here with the product expands and separates into 2 separate logs. So you do log of just A and log of just B. And this right here is just the words for what I said. So just to give you a basic example down here, so if I had log base 2 of 8 times 32, I could certainly multiply 8 times 32 together and get that large number and try to evaluate the log. But if I couldn't use my calculator, easier would just be to use these laws. So if I take the law, because this is a product, I can separate the product with addition. So I can do log base 2 of 8 plus log base 2 of 32 separately, rather than multiplying them together, right? Now I'm dealing with easier numbers. Log base 2 of 8. Okay, so let's go back to yesterday. If I kind of loop around here, this means 2 to the what equals 8. Well, I know 2 cubed is 8, so this log is really 3. This log, again, if I loop around, 2 to the what is 32. Well, 2 to the 5th is 32. So I know that this one, log base 2 of 8 is 3. Log base 2 of 32 is 5. And 3 plus 5 is 8. So just a quicker way, if you're comfortable with logs, that is, a quicker way to evaluate this using the product rule. All right, second law is a quotient. So if you take log of any quotient, so I just did a divided by b, you can separate the quotient with subtraction. So log of a minus log of b. So whatever the denominator is, that's what you're subtracting. So be careful because the order would matter. So quick example, log base 2 of 32 divided by 8. Granted, it probably would be easier just to take 32 divided by 8 because that's 4. And log base 2 of 4 is 2. Like, that was pretty easy to do in my head. But if I wanted to use the quotient property, it says I can separate the 32 and the 8 with a difference. So log base 2 of 32 minus log base 2 of 8. And then I can evaluate the logs separately. So log base 2 of 32, we just talked about both of these. This one is 5, this one is 3, and 5 minus 3 is 2. All right, last property is the power property. So if you have log of a raised to the power of c, you can expand on it by multiplying the power out in front of the log. So c times the log of a. An example down here, if you look at log base 2 of 8, do you know what that equals, by the way? 2 to the what is 8? Like, I already know that that answer is 3. Okay, but I want to use the power rule to show that I could expand on this to also get 3. Well, there is no power. There's no power here. Well, there is. There's a power of 1, right? But that doesn't really change anything. So instead, I'm going to rewrite 8 so that I can see a power. So 8 is what to what power? 8 is 2 cubed, right? So if I just rewrite that, 8 is 2 cubed. Now I see this power. That's like my c up here. I can bring that 3 out front. So 3 times log base 2 of 2. Now, do you know what log base 2 of 2 is? 2 to the what equals 2. This is really just number 1. So 3 times 1 is 3. So kind of a cool application. Now, those are really basic examples. I'm going to do several more that get more detailed. Okay, so you will be asked to use these laws to condense and expand. So let's condense this log. So take a second and look at it. We have 1/3 times log base 4 of x minus log base 4 of y. I should comment because I haven't yet said this, but your bases here need to be the same in order to use these laws. They can't be different. So, okay, great. They are. So first option on this one is, I'm going to just go this way first. Okay, so your first option is this number out front of a log is a power. So if you take the 1/3 and bring it back to be an exponent, okay, so I'm using the power property, and you can use them both ways. You can expand them or condense them. So I brought this to the x, and because there's parentheses around this whole thing, that means this 1/3 power also goes to the y. Okay, so you can kind of take a peek at that. Then notice you have subtraction, right? And subtraction is the quotient property. So hopefully you wrote these down. If you didn't, maybe pause the video and go back and write down the 3 properties. But subtraction means quotient. So I'm going to divide the x and the y. And when you condense these, every time you condense, you 2 things, you get rid of a log. So notice I went from 2 logs to 1 log, and I took x to the 1/3 divided by y to the 1/3. And that is condensed once you get down to 1 log. Okay, a different route that maybe you were thinking about is just dealing with the parentheses first. So because I have subtraction, I can take x divided by y. So I did that over here. Kept the 1/3 out front. Now the power out front, I can bring in the multiplier out front, excuse me. I can bring in and make powers of both x and y though because of the parentheses. So you end up with the same answer, of course, because then you distribute the 1/3 to both. And either direction you approach this question, you should get to the same condensed version. Okay, so that's an example of condensing. You try this one. So pause the video and see if you can condense this. Okay, so first rule in condensing is if there's no parentheses, there are no parentheses, right? You're going to take care of powers first, and then you just go from left to right. But I have to take care of this number out front because it only goes to this log. So if I start condensing the addition and subtraction, this 3 is going to get lost in the mix. Okay, so first step definitely is to take the number multiplier out front and make it a power. So this is 3 cubed. Okay, I did not do anything else. And 3 cubed is 27. You probably can handle that, right? Now I don't have any other multipliers out front of the logs, so I'm done with my power. So now I just go from left to right because there's no parentheses. So going from left to right, I'm adding these 2 logs, and when I add to condense, I would multiply. So 2 times 27, and I'll simplify that. 2 times 27 is 54. And last but not least, I have subtraction, and when you condense subtraction, you're going to divide. And so I condense those 2 logs into 1. 54 divided by 9 is 6. And then unless you can evaluate that, you can stop. So remember, the log without a base has a base of 10, and 10 to the what power is 6. I have no idea without my calculator. And the point of this question isn't to evaluate the log necessarily. So I just condense this down to 1 log. All right, on to expansion. We're going to go the opposite way. So now I have the condensed answer, and we're going to expand on this. So taking a look at log base 3 of this quantity, 7x squared divided by y. Again, there's no parentheses, so I'm just going to separate my pieces. My key advice to you would be separate everything, and then you actually end with the powers. Again, unless there's a massive parenthesis quantity, but there is not. So I have a 7 times, so I'm going to separate the 7 and the x squared. Obviously division, so I'm going to separate that with subtraction. Okay, so that would be kind of my first step, is separate my, and you could do this all in one step for sure. I'm definitely going to take this step by step in case you have any questions on it. So I'm going to take my numerator and separate it from my denominator. Since that's a quotient, I separated them with subtraction. Every time you separate a product, a quotient, you have to bring in another log, right? So it's log base 3 of this minus log base 3 of this. Okay, now I can separate my 7 times x squared, and it's a product, so I'm going to separate it with addition. So add in another log, right? So log of 7 plus log of x squared minus log of y. And then last, and it should be the last thing you do, is take care of this power. Hopefully you didn't think to do that up here, because if you bring the 2 out up here, then you're saying that all of this is squared, but only the x is squared. So that is really critical. So this 2, I'm going to bring out front of only that log and multiply. And that is expanded. And you can double check. There's no other products here, here, no other quotients, no other powers, so you are good. All right, you try this one. And this one is a little more tricky. Before you pause the video maybe and try this, take a look at this. This, because the whole quantity here is in a 5th root. This is the 5th root, by the way. So maybe the first thing you would want to do is change all of this quantity and raise it to the 1/5 power. So if I could give you a little hint there before you pause the video, that's what I would recommend, is change your radical to a power. Because you know with laws, you have a power rule, and you don't have a radical rule, although a radical is a power in hiding. Okay, so now pause the video and see if you can expand on this one. Okay, let's see how you did. So you could do this 2 different ways. Okay, you could just work with the stuff inside the parentheses for sure and expand on it. I personally would probably bring that 1/5 power out first because it's kind of the glue that's holding everything together. And I want to get rid of that glue because I want to expand it. So I would take this whole power of 1/5 and bring it out front since it's a power to all of this stuff, right? So 1/5 times the log base 2 of that stuff still. Okay, now inside the parentheses, I have a product between the x and the y. I have a quotient. I have yet another power. Okay, so I'm going to separate the quotient. Just get rid of that fraction first. Actually, I lied. I did 2 steps in one, but I bet you can handle that. So I separated the x times the y to the 4th with addition, right? Product here means addition, sum. So x plus y to the 4th. And I subtracted with the quotient law. So divided by 16 changes to subtraction of log of 16. Notice with every product and quotient, I brought in a log. Okay, the only other, this log is done. X can't be condensed any or expanded any further. Y to the 4th, there's another power. 16, debatable. I could just leave that, or I could change 16 to like 2 to the 4th. I won't go there quite yet. Okay, so I'm going to bring this 4 out front, right? Because it's a power. And then from there, you could, you actually could probably leave it at this step, or this 1/5 power, now that everything inside is expanded, you could distribute the 1/5 to every single log, right? So 1/5 log of x, 1/5 times 4 is 4/5, be careful there. And then 1/5 times the log base 2 of 16. Last step, which I actually did not show, but again, log base 2 of 16, 2 to the what is 16, that is 4. So this quantity is really 1/5 times 4, which would be 4/5. And I think that would be a great idea for you to simplify that. All right, so quick recap before we move on to graphing. This lesson's a little bit more material. So you have your 3 properties. If you didn't write these down already, maybe pause the video and jot these down. Otherwise, they're in your textbook as well. And we're going to move on to graphing. So graphing logarithms, a little more thought-provoking. Before we dive into one, I want to just show you a very simple example. So back to 4.1, you were graphing exponential functions. So I just graphed here y equals 2 to the x. It goes through the point 0,1. It goes through the point 2,4. You can kind of see that. It had a horizontal asymptote at the x-axis. If I also bring in your inverse properties, so if I take this blue exponential function over here, if I switch x and y, okay, to find the inverse. Now to solve for y, you know you need to use logs because it's an exponent. So I would do log base 2, swing it around, log base 2 of x equals y. Okay, and now you can see in purple, this is the graph of the log function. Now, how did you get that? Well, from the purple, if I go back up to this step before I put it into log form, if it's a little awkward now, but you would test y values probably a little bit easier. So if I put 1 in for y, I would get 2 for x. So 2 comma 1 would be a point, right? So again, if I put 1 in for y, 2 to the first, x is 2. Now if I go over here, 2, 1, you can see that that is a point on my log function. And I could do more, right? If I put 2 in for y, 2 squared is 4, so then I know that 4, 2 is a point as well. Again, if I put 2 in for y, 2 squared is 4. And you can see that 4, 2 is a point on the log graph as well. Okay, we're going to go more deeply into this, but I just want you to understand the log graph is the inverse of your exponential graph. So also remember, you know, the inverses reflect over the line y equals x. So if you envision that line y equals x, you might be able to see those reflections from there. Okay, so if we look at this, I will pick this one apart a little bit further. But if I'm going to just say the function family for logarithmic functions obviously can vary because it can depend on your base. But I'm just going to say log base 2 to keep it simple at first. So log base 2 of x. Okay, and if you want to put this into exponential form, you certainly can. So 2 to the y equals x. If it's easier for you to think about it in this fashion, that's fine as well. I would encourage you to think logarithmically, okay? And really, when you're thinking logarithmically, you're kind of thinking this way anyway, right? So for example, if I said, let's put some numbers in for x here. Well, 2 to the what is going to equal x? Well, I obviously, in my brain, I want those to be powers of 2 because I don't want to have to think too hard. So if you look over at my table here, all of my x values, hang on this last one, right? But all of my x values are powers of 2. 2 to the first, 2 squared, 2 cubed. Now, if you think about it this way, you're also doing the same thing. So, for example, if I put 2 in for x, then log base 2 of 2 is 1. If I put 4 in for x, log base 2 of 4 is 2, because 2 squared is 4. Okay, you can also use this and think it backwards. So pick some y values, 2 to the first, 2 squared, 2 cubed. That's all these values. And then you'll get the x coordinate that correlates with that. I kind of skipped over 1, 0, which I should not. But 2 to the 0 is 1. Anything to the 0 is 1. Okay, now think about this one. Well, is there anything I could put in for y? 2 to any power that's going to give me a negative number? Absolutely not. So that means I can't log negative numbers. And we did talk about this briefly yesterday in the video. So I can't log negative numbers. Well, if I can't log anything over here, then the y-axis is kind of my cutoff, my asymptote, right? My log graph can't go past the y-axis. If I plot some of these points, you can see I plotted those points and connected them. A logarithmic graph is, again, a reflection of an exponential graph over the line y equals x. Okay, now use this thinking. We're going to go into one with a shift. Okay, so I kept my parent function over here in red, just basic log base 2 of x. Now what if I said take log base 2, but instead of just x, we're going to do x plus 2. Okay, you have the knowledge to know what's going to happen. What happens when I take x plus 2 in parentheses? Where do you shift? Right, left, up, down? And hopefully you recall, because it's in parentheses with the x, that we're going to go to the left 2 units. I bet now that I say that, you remember, right? So this opposite sign, since it says plus 2, I'm actually going to the left 2. Well, if I can find my parent function, okay, and I just talked through that, but I'll remind you, if I take log base 2 of x, so log base 2 of 2 is 1. Log base 2 of 4 is 2. Okay, that's my red graph over here. Well, now if I can visualize that graph, all I need to do is take all of my x coordinates and subtract 2. So if I take all of these x coordinates and subtract 2, don't do anything with my y coordinates, I'm going to get these transformed points, right? 1 minus 2, negative 1. 2 minus 2 is 0. 4 minus 2 is 2. Then you can just plot these points. Okay, some of you might be able to just take these points, right, and just say, okay, I'm going to move them to the left 2. Take this one to the left 2. Take this one to the left 2. Ooh, what's going to happen with your asymptote? Obviously, when I shift this to left 2, I'm going past that asymptote. And yes, as you can imagine, that will also shift to the left 2, right? So here is your transformed log graph. Everything went to the left 2. You can probably see that. So the asymptote is always your horizontal shift. So in this case, negative 2, you can see that. X equals negative 2 is my asymptote right there. So that's an important, also kind of a boundary, a key point. How about domain? I forgot to list these on here. What's the domain of my transformed function? This is the blue function, right? Well, domain is x. Oh! Sorry, that's my dog Moose. Domain is x, and everything is to the right of this asymptote. So that means my domain is -2 to infinity. I can't remember where my infinity button is here. There it is. And then how about range? What can y be on this? Well, if you look at the graph, and it's maybe a little bit hard to tell, but you can tell by the arrows, it grows forever up and down. So your range is infinite. So all real numbers, or negative infinity to positive infinity. All right, last log graph that we're going to take a look at. I'm going to change up the base on here on this one a little bit. Okay, so we're going to do log base 3. Please note that I changed from base of 2 to base of 3. Knowing that, I'm going to look at my parent function. I'm going to ignore the shifts for just a second. Okay, and I'm going to say my parent function then is log base 3 of x. So if you think about that, now we have to rethink everything. Okay, so I'm putting in, remember your base is 3, so 3 to the what? 3 to the what? 3 to the what? I'm always thinking powers of 3. So I picked easy powers of 3, and I didn't do very many because they get big quick, right? So 3 to the what is 1. That's always 0. That's kind of a nice freebie. 3 to the first is 3. 3 squared is 9. Okay, so you have these points here. And then if you take a look at my graph over here, I plotted those. So here's 1, 0. Here's 3, 1. 9, 2. You have to get a little creative here, a little bit off the graph. But you can probably see that. And you have the asymptote here as well. Sorry, I didn't dash that in. Okay, now take a second, actually pause the video, think about what are the transformations happening here, and see if you can get that blue graph. Okay, so the transformations on this one, you're going to the right one, right, -1, and then +3 means you're going to go up 3. Okay, knowing those transformations, I'm going to add 1 to all of my x's. So 1 becomes 2, 3 becomes 4, 9 becomes 10. I'm going to go up 3. That's my y coordinates. So 0 becomes 3, 1 becomes 4, 2 becomes 5. Okay, so if you think about those transformations, and then you can also, you don't have to list out the table. You could just take these points and shift them, right? I'm going to take this point. I'm going to go right 1, up 3. Take this point, right 1, up 3. Okay, where does this asymptote go? It also goes to the right 1, up 3. While being it's an asymptote, the up shift, the vertical shift, doesn't really affect it, right? So your asymptote goes to the right 1. Here's your points. Here's the 2, 3. Here is 4, 4. I tried to kind of approximate 10, 5 up there. But your blue graph there is your transformed, right? What's your domain on this one? And what's your asymptote? I should type in the asymptote. So x equals 1 is my vertical asymptote, right? There it is, right there. Your domain is everything to the right of 1. So I'm going to say 1 to infinity. Okay, and you... 1 to infinity. If I can do that, there we go. You can also write x is greater than 1. That's totally fine. Don't include 1, because remember this dashed line will actually never be a part of your graph. Okay, and what's your range? Well, your range, again, is all real numbers. So I could say negative infinity to infinity, or you can just say all real numbers. That's fine as well. So hopefully you're feeling comfortable. Log graphs, they are tough. I will be honest with you. They are very thought-provoking, so spend some time on this, okay? Your homework for today is 2 different worksheets. They're not overly lengthy. Okay, so the properties of logarithmic, this worksheet, just do the odds there. And then the graphing of the logs worksheet, you'll get a practice with those as well. You also have a quiz on Schoology, and that quiz will be 4.5 through 4.8. Okay, below, because this is the last section, I've just kind of recapped all of your homework. It's on the assignment calendar, so you can always look at that, of course. But this is just a recap of everything if you want to make sure that you've been turning those in. The final due date for all of this homework is going to be 11:59 on the day of the last quiz. Okay, so as I'm making this video, I'm not going to verbalize what that day is. Please look at the assignment calendar. Everything is very clear on Schoology and your assignment calendar, but just in case something else changes. Let us know if you have any questions. Otherwise, enjoy doing your homework and taking your quiz on Schoology. Take care.